All right, welcome everybody. Before I introduce the real speaker here, Bob, I'm going to give a quick introduction to Formulatrix and tell you a short story about our history. So I've titled this slide here, Fearless Innovation, Fanatical Customer Support. And that's because at Formulatrix, we love doing really interesting and very difficult engineering projects, sometimes crazy engineering projects that maybe we shouldn't be working on. And then we always work really hard to make sure our customers are successful with our products. So we started Formulatrix back in 2002, so we've been around for 20 years now. We've grown to 1,000 employees, 1,600 customers, and over 4,000 products deployed. One of the things that makes us really unique, if you look at that breakdown of those 1,000 employees, half of them are engineers. So we have 500 engineers working at the company, which makes us have the resources to be able to do really interesting projects. So we started off in the protein crystallography space, developing automation for protein crystallography. And one of the things I love about life sciences is not only do people have super interesting projects to work on, they have the money to pay for them, so that's always helpful. We were lucky enough to be able to take a leading position in protein crystallography. And while we were working on that, we came across liquid handling challenges to automate protein crystallography. So we worked on developing some new liquid handling technology, and that resulted in a micro diaphragm pump we developed, and it resulted in a new product award at S.F.A.S.T in that technology, and the Tempest and Mantis products, non-contact liquid dispensers. And after we had this technology out, Monsanto came to us and they said, well, hey, we need a digital PCR solution, but we need it to be super high throughput and very cost effective. And not knowing any better, we sort of said, oh, that sounds like a fun project to work on. Let's try that. And so we worked on that. We learned a lot about injection molding. We figured out how to injection mold microplates with millions of tiny partitions on them. And the result of that was a Constellation digital PCR product, which also won the new S.F.A.S.T. New Product of the Year award. And we were super excited. We ended up selling that technology to QIAGEN. And then we took, though, all of that knowledge we learned in injection molding, and we asked ourselves, okay, how can we work to make liquid handling even easier for people? And so we've recently come out with two new products. The first product is the F.A.S.T liquid handler. So this is a 96-channel positive displacement liquid handler. So the key to this product is these positive displacement pipette tips that we can make as a consumable, an injection mold at an excellent price. We sell these for just around 10 cents each. And the trick in this is the injection mold had precisions down around 1 micron to be able to get these tips to seal and perform well. And so this instrument then can handle all sorts of different liquids without programming different liquid classes and do transfers down to 100 nanoliters with 5% CVs. You can check this instrument out in our booth. Then the next product we also looked at, and we've actually been in development of this for over 6 years, is an 8-channel liquid handler. And sort of the problem we wanted to solve when we developed this is if you go up to the average bench scientist and you say, here's a stack of 5 plates, can you pipette them for me? Do it as fast as you can. The last thing they're likely going to do if it's a new protocol is go to a liquid handler and do it there. They're going to pull out the hand pipetter and do it that way. So the flow, we tried to put technology in it to solve that problem. So for example, it automatically detects the liquid you're pipetting, so you don't have to program any liquid classes into it. Each of the channels have touch sensing in them, so they can sense the bottom of the labware, they can sense when they touch the side of the labware, so programming plate geometry becomes much easier. And then also it has these conductive strips down the edge of the tips, which allow us to dynamically track the liquid level, so we don't need to know the geometry of the well, and we can track that liquid level. So again, a product you can come check out at our booth. And then another product we've been working on, and we sort of said, hey, autonomous robots are really cool. How can we apply these in the lab? And we sort of had this theory that, well, you can make a small autonomous robot that doesn't take up much space. Much of them, they could work together, multiple of them, to move plates around. But we said, this is kind of a crazy idea. Who's going to buy this? How are we going to convince anyone to buy it? Whoops. Sorry. Yeah. So we worked on developing the Microplate rover for a cell culture system, because we sort of said to ourselves, nobody's going to buy this until we show it in a product that can work. And then we were talking the other day to Bob from Beam, Bob Gantzer, and he said, I have an idea of how I could use these. Let's me introduce Bob Gantzer from Beam Therapeutics to take it away from here.
Excellent. So I'm going to move around a little bit. So very excited to be here. I love SLAS, and I'm actually going to talk a bit about how SLAS as a conference actually plays into this story and how we use the rovers at Beam. But it's just been great to see like at least half of faces in 3D as we're here at SLAS. And so it's weird to not start a presentation with, can everyone see my screen? Because now everybody can actually see what we're doing here. So today we're going to talk a bit about, I'll do the intro of Beam Therapeutics because they let me come and talk, so I've got to plug the company a bit and tell everybody about what we do and that we're hiring. I got to get that part in. And then we'll talk about our lab automation strategy, which this is a bit of an update from last year. So if you saw our presentation at last year, we spent a lot of time talking about how Beam approaches our strategy around lab automation. And then we'll talk about SLAS, or the Catalina wine mixer of lab automation, and kind of why it's been important in what we try to do in collaborating across the organizations that all come to this conference. Then we'll show what everybody wants to see, the rover video, right? See the rover out in the wild. And then we're going to change gears, and I'm going to talk about a different problem, what I'm calling the last mile problem of experimented or automated experimentation. And then we'll talk about what we think the new journey for lab automation might look like with some of the technology that we'll talk about today. So first, Beam Therapeutics. So I used to have to start this slide with, okay, raise your hand if you've heard of CRISPR. But in the last 2 years, I'm pretty sure everybody in this room now has heard of CRISPR. And so when you think of CRISPR, the analogy that they give is it's molecular scissors, right? It goes into the DNA, it cuts the double helix. When the double helix is open, then you can do a lot of cool things with it. Insert DNA, delete DNA, knock out genes. Well, when we look at base editing, which is what Beam Therapeutics does, if you carry on that same analogy of scissors, we're more like a pencil and an eraser. We can go into the genome and change single letters of the genome in a precise location without inducing a double-stranded break. So how we do that is kind of the overview here, where we take that CRISPR-Cas9 molecule and we modify it so that it doesn't do any cutting, but we're still able to use that guide RNA and Cas9 targeting mechanism to then target the genome precisely where we want to go. And then we tether to it a chemical modifier that'll go in and perform the chemical modifications that you see on the right-hand side of the screen. We'll do a deaminase where we can change a C to a T or an A to the G in the genome really precisely, again, without inducing any double-stranded breaks. That's all the science I'm going to get into. We'll go to the robots now. But if you're interested in Beam Therapeutics, just go to beamtx.com, and we've got all of our papers that the company was founded on, and there's a lot more material on the actual underlying science. So Beam's automation strategy. I'm getting tired and a bit embarrassed of this slide because I've shown it way too many times now in my life, where this is actually one of the slides I showed at my interview at Beam about almost 3.5 years ago, where I said, all right, here's where I see the journey of automation happening. I see, most of the time we start with the manual process, and that little cartoon there says, we couldn't afford one of those cool PCR robots, so we just got an undergrad and a cardboard box. And it just seems like that's where everybody starts your journey, right? You start in manual, then you do the semi-automated thing where you bring in the liquid handlers and you put it on the bench. And then what we were saying is at Beam, we want to push it to fully integrated, right? We want to make sure that we're really pushing it to integrated solutions for all the advantages that we've talked about and that we all talk about on the floor during this conference. But what's more is we've started to really evolve our thinking in that we don't really want to just integrate devices. We want to start to redefine what it looks like to have an integrated laboratory. And so really what happens now in a common lab is sometimes you do the semi-automated thing, you bring in the Hamilton, the Biomech, the TCAN, the Prime, the Formulatrix stuff we'll talk about today, and you stop there. What we're seeing more and more is people go to the fully integrated route and then they'll stop there. Well, what we really want to do at Beam is view what are all the components that are needed to really make a fully integrated lab. And that's not just hardware. It's not just slapping a robot in the middle of a bunch of devices. It's also not just the software part of it, but it's also the science. How do we bring all three of those pieces together into what we're calling now the integrated laboratory? So unveiling, this picture is from about a week ago. This is Beam's new integrated research lab that we just built in Kendall Square and literally a week ago was finished working. So this is about as shiny as it'll probably ever be. And what we view at Beam is we really want to embed automation and robotics in the core of all of our research functions that we do. So NGS, delivery, discovery, platform, those are all ambiguous public names for what we're doing. But as you can see, we're really trying to embed automation and robotics in the middle of everything that we do and touch all of the research across the organization. For us, this lab isn't going to be behind a lock and key that's only run by high-throughput research automation engineers. Our goal is how do we make it accessible to a bulk of the scientists across our organization? So here's kind of a panning view of where we started. And if you look at this lab, we've got 3 integrated systems in there. Ursula, Gaston, and Tamatoa are their names. Yes, those are all Disney villains. There's a theme there, and during the Q&A, if people are interested, I'm happy to touch on why that is the case. But Disney villain names for all of the robots. And what you can't really tell from the schematic there is all of those are actually very unique pieces of equipment. They all serve unique purposes, though they kind of look the same. They've got significantly different integrated devices and different groups that they're serving. But what's even more challenging is they're not just serving one group, they're serving overlapping groups, right? So, we had 8 different groups that we're trying to serve across 3 different platforms. How are we going to make that work? Enter the rovers. So then we start to think about, okay, we've got these islands of integration, these integrated platforms. How do we start to integrate our integration? And it all started at SLAS. So this is actually a picture of Matt Humes, who is our Associate Director of Automation and has been with me at Beam from day one, basically building out this crazy lab that we're working in. And this is me taking the video, and if you could hear the sound, my goofy giggle is going in the background as we're actually seeing the rover for the first time and then videotaping this at SLAS 2019. And so we're just laughing at this concept of this rover that we've never seen that Jeremy and his team were crazy enough to build. And so that night we went out brainstorming, and by brainstorming I mean we had cocktails at the Hamilton party, right? And so as we're brainstorming that night, we just can't help but think, how could we use these? What could you actually use these for that would be worthwhile and justifiable? And that's when we started coming up with the idea of, could we use them to start to connect these islands of integration? Now keep in mind, at this point in Beam's development, we had 1 Hamilton. And it was in a box. It wasn't even unloaded yet. But we were still thinking ahead to how would we use crazy rovers to integrate islands of automation that we hadn't even built yet at that point. But it was just kind of this idea that we had going from day one at Beam. And so what we did is, we just kept kind of thinking about it, talking about it through all of our kind of planning sessions. And then the day came where our leadership said, okay, Bob and Matt, you guys get to build your automation lab. Meet with the architect and start to give them the list of things that you would like in your lab. So we go through the things where like we need big doors, right? We want floor-to-ceiling windows. We need access to utilities. I need a Rover track hung from the ceiling. I need this and that. And the architect's like, wait, what? What was that last thing? You want a Rover track hung from the ceiling. And so it's an architect. We just played off like that's a common thing that you do in an automation lab. It's like, yeah, of course we do. And so we're explaining it to him like the train tracks at one of those hokey Midwestern restaurants that kind of just goes around. Like that's kind of what we were looking for. And so sure enough, we tricked the architect into designing this for us. And this is some of the earlier renderings of what the lab would look like. So it's one thing to trick an architect into going for this. It's another thing to trick our CSO, my boss, into actually signing off on this, right? So I basically go into his office and I give him the same justification I'm going to give you today as to why this Rover system makes sense. And sure enough, he actually says, okay, go for it. And I just want to throw out there that really at Beam, one of the things I really appreciate is the fact that no one's done it before isn't a reason to not do it. And so it goes back to one of our core values of fearless innovation, and really our organization and our leadership really supports that in saying, go for it. We'll see if it works, and you've got the right justifications for it so you can really try these things. And it's one of the things that I think is really special and that we really need to embrace more in lab automation. All right, so we've got the architect tricked. We've got leadership on board. There's only one problem. We haven't talked to Formulatrix about any of this yet. They don't even really know that we're having these conversations or that we've started to put these designs together about using the Rover this way. So we called Jeremy and his team over to Beam when we were at our old location and start to actually walk them through this plan of, hey, we want to hang them from the ceiling. We need elevators connecting our integrated platforms. We need open APIs that we can access from our various pieces of software. And again, they were crazy enough to say yes and go along with us on this journey and then fully embrace the challenge that was ahead. So here we go with the final unveiling of the Rover system. So this is the first deployment of it that we've had in our labs. As you can see, this is actually going from Gaston up the elevator. Where it starts is actually at a plate handoff location where the precise arm in the central robot can then hand off plates. The spatula from the Rover can then grab those plates, pull it off the nest, and then put it onto the Rover. And the Rover can now drive it across the track, hanging from the ceiling over to the other system, go down on that elevator, put it into the plate handoff. The centralized robot then on that system can grab it. And all of a sudden now what was two disparate systems doing two different types of technology, two different types of science, are now completely connected. That's that, and you can go see it in action at the booth downstairs. Okay, so it looks cool. Like, we love that, right? Like, they came together beautifully, but it's got to do more than just look cool to actually be worth anything. So why? Why the Rovers? And I think it's important to point out, like, we're not the first people to do this, right? Like, connecting these islands of automation isn't new. I think it was 2 or 3 years ago, Lilly made a huge splash with their automation investment, their track that's shown here, and the amazing lab they built. Right up the street, Ginkgo's doing a similar thing with their COVID lab, again, connecting islands of automation via these track systems. Zymergen's been doing it for a while. Like, this isn't unique, connecting these islands of automation. It's just the Rover concept itself is a little unique, as opposed to maybe the traditional track route. So when we look at the benefits of that, we think one of the key ones is cost. Really, the components that go into this, for example, the track that was actually running across the ceiling is actually relatively inexpensive. The Rover components themselves on lab automation standards are also relatively inexpensive. You got to put that caveat in there all the time with lab automation standards. But so compared to what it might take to integrate some of the other islands, it's actually a relatively cost-effective way to do some of these integrations. Another one that we really love is the vertical integration. So our new space is in Kendall Square in Cambridge, where real estate is, if you can find it, very expensive. So when our leadership granted us a certain amount of space, we needed to make sure that we were fully utilizing all of that lab space that we were being given. And so by us being able to go vertical with the track, it then allowed us to use space up in the top of the lab that wasn't previously being utilized. Additionally, now you don't have to walk around the track to get to like the other side of the lab to access your automation. And really the footprint on our automation is minimal. That plate handoff is really only, I don't know, 1.5 feet deep and maybe 10 inches wide. So we're not giving up much space on our integrated system, and we're not giving up much space in our lab, and now all of a sudden we still have full access to all of our platforms that we needed to because it's so lightweight we can just hang it from the ceiling. The big one, this is the one that I really do think sets it apart from some of the other options out there, is the flexibility. We're now connecting Ursula and Gaston together, but we're going to connect the rest of the labs and other things together via these tracks too. And it's all you're doing is hanging pieces of track board that weigh 40 pounds or 60 pounds each connected to each other. The first install of this system, they've never done this install before, of 2 elevators, and the track itself took under a day. For them to connect the next system is going to take a few hours. To just hang the track, put the elevator in, and throw a few more rovers up there, and you're done. You don't have to think ahead about utilities. It literally just plugs in to one of the charging stations up there. So you're not having to run air everywhere. You're not having to build out these tracks with, knowing where you're going to be 10 years ahead of time for expansion. These things can literally then just be piecemealed together in a really flexible way that just kind of gives us the freedom to do what we wanted to do. If we wanted to tear this track down and move it 6 inches to the left, we could do that in a matter of hours. It wouldn't really be a challenge. I don't know that you can say that for some of the other approaches. And then the last thing I think is some of the redundancy that it provides. So, if you're looking at the track system, I don't know what happens if a penny gets stuck in there and it goes down, right? Is your whole system out? Can all the tracks run into each other? I don't know how that works. Even for some of the precise arms on the Roomba things that drive around, that's, it's hard to get a swarm or a fleet of those things just because of the cost that's tied up into them. With the rovers themselves, a unit goes down and you just climb up on a ladder, which is kind of a pain, and you just take it off and you ship it to Formulatrix and they ship you a new one. And you're still running with however many you had up there before. Or if you need to grow your capacity, you just buy a few more of those. And again, on lab automation standards, they're really rather cheap to throw additional capacity at it. And then you've got this redundancy built into where the hardware itself is housed. So why even integrate the islands then? So that's the justification for the rovers, but why even go through the work of integrating the islands? Well, for us, this one was a pretty simple calculation where we were running a batched approach before. Ursula was doing DNA isolation, quantitation, normalization. This is when we had one system. We'd break the system down, then we'd do NGS, and then what you were running was you would basically just be doing 2 parts on this system in this batch configuration just because of the limitations that we had on some of the hardware and having just one system. And so what we were able to do is 10 plates, let's say 1,000 tissue samples or something like that through NGS in 13 hours. Now if you can do a continuous process where as soon as that first DNA plate is ready, it can then get sent to NGS and start its processing, then you can start to tie all of this together in a way that we couldn't before. Whereas before we were doing a single DNA plate and we were waiting until the last plate was done until we could start everything, all of a sudden you start to tie all of these together and you start to get some real efficiency gains. The other thing that we like about it is that it gives us access to better device utilization. Now if we're connecting all of these integrated systems together within a lab, you're not buying, I can't remember the name of the awesome high content imager down there this week, but you don't have to throw 3 of those on each of your systems, right? If you just want to purchase one for capital, put it on one system, all of a sudden now you can just use the rover to drive your plates over there when you need it. So we can start to look at the equipment within this integrated lab as just one lab that now has fully integrated, automated access to anything because now we can just rover plates over to the devices that are needed. So we're building less local redundancy within our systems themselves. So this is kind of the one where I get a bunch of questions about what is our strategy on how we do this. So how do we integrate some of this stuff? And again, I go back to kind of the hardware, software, science side of things and how we view an integrated lab at Beam. And when it comes to the hardware side, we outsource. There's a whole floor full of people focused on hardware. I don't really want my team caring too much about that. I'll let everybody in the room down in the vendor shop make the best product and compete for that. So at Beam, we're just finding the best partners in Formulatrix, in Hi-Res, and some of those that we've partnered with over the years to really deploy our hardware for us. I don't want my team focused on that part of it. When it comes to the software side of things, Beam gets a little bit more involved, but we still pick the right partners, right? When we're looking at the data side, we build all of our stuff on AWS. We use Benchling, as I've talked about before. On the scheduling side, we're using Solario for a lot of this, or the Fleet Manager API suite. And then for the orchestration, we use Artificial, and then Beam, as you can see, is kind of connected to all of this. We build our own software to tie it all together and to really make it custom for what we do here at Beam. Now, the science is where I really want my team to focus. This is where the real challenge comes in modern-day automation and integrating across organizations, because it becomes a science and a people problem, right? How do we interface with all of these different departments successfully enough where really your common-day scientist still does not have lab automation experience? So how do we build a group of super users within Beam that can then help us really get our message out there of the benefits of automation, and then start to get groups within Beam very comfortable with using these integrated platforms? Because again, we're not asking folks to use a liquid handler. We're asking you folks to use Rover integrated complex platforms. But again, I want my team focused on the science. So when I look at what I think my team does, it's kind of that combination of, I don't know if you can read this, but it's software, hardware, and science. What I want my team to do is focus more on the science part of this. What my team actually does is liquid class development. And that's where we started to think about, okay, why is that? Why is such a bulk of my team's time spent on just liquid class development and just that minute detail of experimentation? And this is kind of where I came up with what I'm calling kind of the last mile problem. And I think everybody's seen this. There's been nothing talked more about than logistics and supply chain during the pandemic, right? And so as you hear more and more, I don't know, maybe this was just ingrained in my mind, but I start to think about this first and last mile problem where when you're transporting anything, that first mile is always the most complex because you never know where it's going to start. The middle part is very efficient because you've got the metro. I guess not in Boston, but in most cities, you've got the metro where it can then efficiently transport people to where they need to go in bulk. And then you've got the last mile problem where you never know where people are going to go, so it's relatively inefficient. So this is my journey here today, actually, coming from Beam's old site, where you can see I'm walking 10 minutes to a T stop. I'm taking the T relatively efficiently through the city with hundreds of other people. I took an Uber today, but this is an example. and then you walk the last part, and then you can see that first and last mile of the journey are the most complex. Okay, everybody gets it, right? So why am I talking about that? How does that equate to automation and experimentation? Well, I think in the same analogy, experimentation is really the first mile of lab automation, right? You never know where you're going to start. You don't know what variables you want to throw at your experimentation. You really don't know the questions that your scientists are going to ask. The middle part is the metro. This is what we've got figured out. I think in lab automation, right, this is a very efficient process. We can take any device on the floor down there, throw 300 plates in a stacker, grab a scheduler, throw a robot, tie it all together, and it's fine, right? We can efficiently process these multi-thread experimentations. That's not the issue. But then the last mile gets to be when the liquid touches the tip, right? Is the experiment actually being performed how you think the experiment should be performed so that the data you generate is worth a damn? And so that's where we actually end up running into the issue a lot, is this last mile problem. And that's where we got really excited about this new line of liquid handlers from Formulatrix, where if we can start to eliminate that from some of our issues at Beam, where all of a sudden when we're looking at the F.A.S.T, if we've got the opportunity to just throw a plate on a liquid handler, press go, and it's going to transfer the liquid that we ask it to transfer, regardless of viscosity, of cell density beforehand, of any of the variables that a scientist is going to try to throw at any experiment that you've already made, then all of a sudden we're not having to worry about that. If we've got the flow I8, and all of a sudden now we don't have to dictate to our scientists that, hey, everything has to start with 110 microliters, or it's going to break my liquid classes because I haven't taught my liquid depths, or something like that, right? If it can sense on the fly when evaporation happened through your process, if it can sense, when somebody didn't really think how much they were throwing in there, if it can do all your liquid class development on the fly. When you're looking at this, you've got two different liquid types, and all of a sudden now it'll adjust how it's aspirating and dispensing. If you don't have to worry about what your scientists are throwing at the experimentation, then it really changes how you think about this first mile, last mile problem. We'll let it finish dispensing. So all of a sudden now, my team's not focused on liquid class development. My team's now back to the science where I want them focusing on interfacing with our scientists and really thinking about how do we make the best utilization of the automation that we do have. So the journey then changes. Your first mile problem becomes that much more important, where how do you interface with your scientists to make sure that your experimentation is translating over, or their experimentation is translating over to the automation as you want it to. It really makes this first mile that much more important, but that's fine, that's science, that's what we want to focus on. The metro is now the same as it has been before, but now you throw liquid handlers in there as being a part of the process that is efficient instead of part of the last mile that's causing you burden and pain and is being like the worst part of the process. It's now into the metro system where it's as efficient as everything else is. And now your last mile changes. Now your last mile is the data. And now it's, okay, I've got this awesome data that I'm now generating at scale. What do I do with it? How do I act on it? How do I make meaningful insights? Which is great. Now you've got this awesome data instead of being worried about, is my data that awesome? So it just changes now. You still have a problem, but the problem is one that you want to focus on. The problem is a scientific problem. And so we see now the journey within lab automation being one where we as engineers in our room at Beam really want to keep focusing on the science, because that's how we make Beam a better therapeutic company. That's how we advance our science, and that's ultimately how we help patients, is by focusing on what really matters and then relying on our partners to take care of the rest. So that's my talk. So that's what we're excited about for our journey. I just want to say thank you to my team up there, particularly Matt Humes, who, as I said, has kind of been with me through this whole journey and helping me build everything. So, thank you. So I think we have time for questions. We did okay on time. Anybody have any? Happy to answer anything that comes up. Yes? Yeah, good question. So how we handle this now, and this is kind of an evolving target, to be honest, and it is probably the most challenging part of doing this, where the fleet manager software, which runs the rovers, is great. They've built an API layer for us that really then they can allow us to control what we care about, and they take care of the rest, right? So I'm literally sending a call to Formulatrix Fleet Manager that says, take a plate from Ursula Nest 1 to Gaston Nest 2, and it's going to take care of everything else. It's going to take care of what rover's closest, what rover has the most battery life. How do I, if a rover is getting low, drive it to charge itself up, right? How do I handle all of that? So they take care of everything, where I'm literally then just sending those API calls to say, go to these locations. The challenge gets to be then, how do you orchestrate that with the other integrated devices below? And so, as I mentioned, we currently use high-res for our scheduling, and we actually like having the local scheduler still have control over the automation that it's running. So Ursula or Gaston can still be locally scheduled and running optimally to what it's trying to do. And so what we end up doing is sending rovers to what we call the parking lot. So when it's done at one system, it sends it up and actually moves it halfway to the track in this area where they can navigate around each other. And then what it does is it actually sends a command to the scheduler on the system that it's going to say, you've got a plate that's ready, but you say when you want to bring it in. And so then that local system sends a call to that rover to say, I'm ready for you now. I've got a landing position, come land it. It'll grab it, and then it'll just orchestrate it into all of the schedule that it needs to. So we give local scheduling control to each of the small integrated devices using kind of a parking lot push away, pull in model for how we actually orchestrate a lot of these things. And then really we utilize the API through Solaro, where we can just then, from one system that's running, we can send an API call to the Solario scheduler, place orders via that API call within the local scheduler, and then we just submit an order to that and we hit execute. And then a part of like the first move on that Solario method is bring in Rover. And so then it knows to call the Rover in from wherever it's at. Does that make sense? Yeah, question? Lowest guy on the totem pole grabs the ladder. So there's been, we haven't run into too many yet where we've had to go up there and start fishing the rovers down. They do have really good, robust air handling. We're still kind of, it's one of those where we're working through everything that could come up, right? Like there's always scenarios as you push it to the limit, which is what we're trying to do now to really test it out, where you say, okay, I'm going to throw a plate on every single one of these rovers. I'm going to have them in action as much as I can, and how is it going to handle when it needs to take one out of commission and then charge the battery, right? Like that's something you've got to think about how it's actually going to charge the battery during these operations. And so that's when we have like fall overs within Solario too, where it's like, okay, take this plate, put it back into storage. If the first API command of the fleet manager is a rover available? And so if you hit that 3 times and you get a no, then Solario has auto air recovery that we're able to say, okay, run this script, take it, put it in the fridge, and then really wait for either user intervention or 10 minutes later, try again and see if you can still send it over. So honestly, we're still working through all of the scenarios, but we do rely a lot on, the thing I love is that it's all API driven. So it allows us to just do it via software, which just makes the air handling so much easier if we can just hit API calls and just get like the air code back that we're looking for. Yes, in the back. Yeah, completely correct. And I'll repeat it for people that couldn't hear. The question was, okay, yeah, you're trying to strip away redundancy, but redundancy is necessary at times, right? Particularly if you're running a multi-hour experiment that's Rover integrated across 3 systems, right? And you've got a plate sealer that goes down on Rover 2, and it's just going to cause a big traffic jam. True. And we try to thread the needle there. I mean, right, we're all capital constrained where you can afford redundancy in some places, and then when you don't, you take on the risk associated with it. Like if you look at each of our systems, we've got the exact same cart on all 3 that has a sealer, a peeler, a centrifuge, and a labeler, because we find we use that all the time, every day. And so what's nice about the high-res system is now we can undock that cart and put it somewhere else if we need to, or build another one of those redundant carts, because those are ones where it's like all of a sudden if you don't have a centrifuge locally, right, it's one of those that you want, then you're out of luck. If it's something like a high-content imager, which I was talking about, right, like if you're going to drop 500K or $1 million on something that you're integrating, it's harder for me to then justify that redundancy for those kind of items, though if that's the science that you're doing, maybe you can. And so that's kind of all I was saying was you can throw more specialty stuff at it, but that might mean if you're running those assays, you do have to be a little bit more present in knowing what's going on. The other thing I'll point out too is we're working to do a lot of, with artificial too, just on the fly monitoring too. So the trick is like, if there's an error, do you know it happened so you can go in there and resolve it, right? So we've got kind of constant monitoring that we're looking at as far as like what devices are working, which ones aren't, and then also working on getting the error logs to a place where we can start to really track, okay, is this going down more often, and is this what always gets in the way, so maybe we need to buy more redundancy. But it's a good question. It's a balance with anything. Yeah? Yep. Yep. Yeah.
So I've seen some great videos.
Thank you.
So how do you buy that?
For the videos?
Yeah.
As long as I say, hey, Beam is hiring, go to our website, they'll kind of let me do whatever I want to these days. So that's why I had to put it in at the beginning and just say Beam is hiring. And again, so if this is interesting, that's the plug. And then they let me do cool stuff. Yeah.
But the other thing, so with like the supply shortages and things like that, it's like everybody, we're very fortunate that we've been able to work around it with our chips and things like that. But I noticed in your lab, I think you have like, so your first system had 2 bandages.
Yep.
And now I think you have
Some fluents.
right?
Yeah.
So was there kind of like a story behind that?
You're trying to get me in trouble, huh? we'll just say, it's,
Some people like
yeah.
again for the tips or
Yep.
something. So I was wondering.
There's pros and cons to both, and honestly, part of it came down to diversification of supply chain for a while, to be honest. So you said you managed the supply chain well and didn't run out of tips. I don't know that I can say the same thing, to be honest. And then ship them to you? Oh, there you go. Well, now I know. A year too late. But yeah, so I mean, again, it's diversification in what we're doing too. I mean, that's why, yeah, Hamilton, TCAN, and Formulatrix, right? I mean, putting them in, and then they all have their sweet spots. We all know these devices do some things better than others. And so again, the benefit gets to be, okay, well, we've got a Hamilton on one device, TCANs on the other. Well, cool, let's use the Rovers to send the samples to the best device for the purpose that we're trying to do. And the same thing with, I didn't see it too much here, but there's F.A.S.Ts integrated into these systems too. So similarly, the F.A.S.Ts are on Gaston for a lot of our NGS workflows, a lot of our kind of goopier samples that we don't want to work on like liquid class development for. So again, I think having the Rover approach allows you to put the right tool in the right position, and you don't necessarily need to get bought into a single ecosystem and then just live with the warts of one particular system. Instead, you can really just build the best devices for your science. And again, it kind of just bring it back to the science part. Yes?
So you showed a lot of automation that you have, and many times you said like time is invested in liquid class development or some other thing. What about maintenance? How much time do you guys spend on maintenance, and what do you do to reduce that time, or what resources are you using to manage that?
That's a really good question. That gets to be tricky. We are bringing in, did I mention Beam's hiring? So if I haven't, we're bringing in some internal Beam resources to help us with our own maintenance of the core of the instrumentation here. So it's one of those hybrid approaches. Of course, we do the service plans for the ones that matter, where we get value from it. And so that way, if we know we've got a good relationship with a company that we can trust, then we will do the service plans and outsource a lot of that. And I mean, I'm from the Midwest, and my last gigs before this were in Indiana. It's much easier to get service in Boston than it is in Indiana. So it actually has changed our calculation a bit, just because we're so close to, we can drive to Formulatrix in 40 minutes from where we're at, right? So a Rover goes down and they're literally at our door an hour later swapping one out for us, which is nice. So I think geographically it matters where you're at too, but it's some sort of combination of partnering with the hardware companies. Again, at this moment, I'm not sending any of my team to go do the Hamilton hardware course, right? Again, we're a team of 5.5. I count myself as half a person these days. And so we're not a big team. So I can't dedicate, 2 people just to service all the time. So again, when it comes to hardware, we outsource it. And we just really rely on partners that we trust to be able to handle some of that, to really make sure that our team can focus on the science part. Yep. Yeah.
I really enjoyed this talk, and I like how you compared the Rovers to the Microplate rails. Have you also looked at mobile robotics and how they compare to each other?
Yeah, like the Kevins and like what Fraunhofer was doing and that kind of thing. Yeah, I mean, I think to each their own. It depends on what you're trying to do. The thing I like the economics of the Rover, to be honest. Like, I like that, I don't know the price tag on a Kevin, but you've got one of them, and it's got more flexibility, right, than a Track does, right? You can drive that thing anywhere you want to, which is nice, but I could only afford to maybe get one, whereas I can get a swarm of Rovers for that. And so you get some parallel processing that's nice that you can do at that point. I'm also excited with, there's a lot of new arms downstairs that are getting cheaper and cheaper. So why put necessarily like an expensive arm on a base when maybe you could take an inexpensive rover, drive it over on the bench to an inexpensive SCARA and just start to feed your devices that way too, right? It could change the way that you actually kind of build out some of these integrated lab platforms. I mean, I would have made some changes in even how we built this out, knowing how instrumental the Rover platform will be and how we deploy it. Like I might have put more storage central, right? And then use the rovers to kind of deploy it in that way, as opposed to more local on devices and things like that. But I do see a future in which you can have these on the bench top, just driven over to devices and just have, you know, a cheap arm just feeding that device. Yeah. Yeah, event simulation. So yeah, I can repeat it too. For a discrete event simulation for understanding the processes. Yeah, there's a full simulator that comes with the Rover platform, which is actually awesome. So they were using it for just all of their bug detection and path planning and things like that. But we've got full access to a simulation of this entire thing. So you take that with, you know, you can simulate any of your local schedulers. You can send those commands in back and forth from the fleet manager simulator, and you can simulate entire workflows now. Now, I mean, it's very new where like you actually see them moving around and how they're going to do it, and you get air logs back. Like it's not going to give you a Gantt chart or anything like that yet of how it integrates. But yes, you can fully simulate the rovers. Yeah. At what point do you need to throw 2 more rovers on there, right? At what point are you constrained and it's causing an issue? And that's the thing when I said on redundancy, like, again, it's, okay, I don't have enough, let me just place an order, take 2 more and hop on a ladder and throw them up on the track. And that's it. And you've just, you know, doubled your capacity, tripled your capacity, depending on how many more you want to buy. Yes?
Question on your first and last mile problem. So you run some kind of pilot project or proof of principle on that. How many different parameters do you need to measure to overcome this variation on that?
For the liquid class development side of things? Yeah. So yeah, we worked pretty closely with, particularly on the FAST and still with the flow. So we own a couple FASTs. We don't own any flows yet at Beam, but have working with them on some of the development side. And I think on the FAST side, I think Formulatrix had us come in 2 years ago or so, maybe even to start to look at it and test it. And so it was nice. We had a unit in-house before we actually purchased it for, I don't know, Daniel, what, 6 months, 8 months, where we got to just kick the tires on, you know, here's every, you know, variable we might want to throw at it. Here's, you know, we run in and we do a lot of cell work, right? So we're processing a lot of transfected cells with our base editors that we're then lysing, taking through to NGS, and then see if we edited the cells where we wanted to. Just the variability in this lysate that we get from our scientists, depending on like the cell type, the confluence, the, you know, the toxicity of maybe anything they've put in there, is just wildly different. And so our liquid class development time for just trying to figure this out was just like throwing a dartboard in the dark. Like we just really could not figure this out where we weren't getting these goopy samples from the scientists and like, okay, cool, we can handle that. And then we get ones that weren't, and it's like, well, we can handle that too, but we gotta know what you're sending us. And so it's really these devices have freed us of that, where it's now, you know, with the positive displacement of the FAST, we're able to then just pull up whatever's in there and transfer it and just know that when we get a null data point at the end, it's not from a transfer that didn't happen. It's a legitimate data point that we can use and move on from. Yes?
So in your presentation, you're showing that all these three modules connected, you know, with the rover.
Yep.
Basically, it's still at point to point, right? It's moving from one point to one point. It's one-way traffic. Have you considered about doing a traffic that was a two-way traffic?
So it's two-way. This is two-way traffic. Okay. So yep. So it looks thin, but it's got 2 lanes basically, and a passing lane even too, where if one's sitting in the parking lot, they'll drive around each other. But it's fully two-way. So we can send it from Gaston to Ursula, Ursula to Gaston. We'll add Tamatoa in the mix. We'll be able to go from any of those that we need to. And that's another benefit I didn't talk about. There's, you know, another cost-effective way of doing this is you have these little rail systems, right, that just send from one to the other. And that's great if you've got 2 systems right in one rail. But all of a sudden you've got 3 systems, and all of a sudden you want to connect A to B, B to C, C to A, all of those. You're at what, 6 rails? all of a sudden you throw another one, and how many rails are you doing? Like, so if you're just going point to point with some of these rail systems, you lose scale as you grow, where again, the flexibility of some of these Rover track systems, I think, become really appealing for that. And eventually we've talked about it, it's like, do we just make it like a racetrack around the outside or something? And, or I don't know. But the fun thing is we can change it, and we've got flexibility. Yes, in the back. It's a great question. Right now we're keeping it at a low-ish number just because we're kicking the tires on this. I mean, this is the first time it's been deployed. So right now in any given workflow, we might start with kind of the 10-plate protocol that I talked about, where we'll maybe start with a couple thousand tissues that we load in, put them into, eventually isolate DNA, normalize, and we'll send maybe 10 plates in any given day over to the NGS system and run NGS. So that's the scale we're at now, just to make sure we can kind of work out all the bugs before we start to throw more at it. Where it starts to get fun is what I started referencing before, is can you change the way that you actually even load all of your systems? Can we now, instead of putting Steri stores, microserve, ambi stores on every single system, can we just put them in a centralized location? So now you're just loading just a stacker of deep wells. And now every time a system needs a deep well, it just calls the rover to bring those in. And that way it makes your inventory and loading that much easier, where you can just go into one centralized location within your lab, just make sure that stack is full, and then just rely on the rovers to get the plates where they need to go at the time of delivery. Now, if you start doing that and you're looking at like every plate that you need for every experimentation, those numbers start to really add up, where you'd start cranking through them, and we'd need to pressure test that a little bit more. Any other questions? Make a what? Sorry.
A tow truck rover.
A tow rack rover? Oh, there you go. Yes. Yeah, I've even thought about that. It's got the little lights on it, and it's just, yeah.
Yeah, I don't know, maybe Formulatrix is working on like speeding up the rovers, because maybe this is first generation. I don't see it's as fast as say like an arm or on a rail or
I mean, the thing that's maybe a little slow is when it does the little plate gripper thing and then goes to the elevator. The speed going between systems, I'm not actually too concerned about, to be honest. I mean, when you actually map it out, that's not a limiting factor for us by any means. And particularly when you're talking about the arm, what I love is that it's actually pulling resources away from that arm. Whereas if I was to throw more science at an individual system, I mean, a lot of times that centralized precise arm becomes a limiting factor for us if we look at what's really holding things up. And so now, again, the fact when it goes back to continuous processing versus batch processing, I'm not as worried about the time it just takes to shuttle back and forth, because it's then taking it to a system that might be fully available to be used. And even then, you can even start to think about the experimentation you're running. Can you run your lab as a batch of things, right? Where like the same assay can be run on Ursula and Gaston, and then you just orchestrate from a high level where it's sending the rovers, and now you're getting infinite efficiency, or not infinite of course, but you're getting twice or more efficiency from what you would process than you would if it was just, I have to decide as a user where I want to load it, or I have to manually split between these two systems or something like that. Yeah, question.
So Disney villains?
Disney villains. Okay, yes. So the question was Disney villains, and I've brought this up before. It actually goes back again to when I was hired at Beam. So people, I feel very fortunate to work at Beam and to be in an organization where my boss, Pino, the CSO, brought me in as employee 25, 26, as a head of automation, which is pretty rare, right? To bring somebody in that early within an organization and say, automation is going to be a cornerstone of how we execute science at Beam. And so people are like, you're so lucky. You got to start from scratch. I was at a bigger, older company before where it was hard to move things and change things. So people are always like, oh, you had it really easy. No. I mean, it's never easy. What we do is never easy, mostly because it's hard to, again, convince scientists to use some of this. So one of the top scientists, I think, in the world, she was in my interview panel, and about halfway through the interview, she looks at me and she goes, I just don't get why we need you. Like, this is the level of pushback of like, why do we need lab automation in experimentation? She comes from a world-class lab under world-class professors and has just been taught this like academic way of executing experimentation. And so legitimately, a requirement of my employment at Beam is that this individual gets to name all of the systems at Beam that we have, And so now, early on, she named them all after villains, just to kind of get the point across that automation was not her favorite thing in the world. Since then, we have now convinced her otherwise, and she's one of our biggest proponents, but we like to continue the villain trend going just to prove kind of how far we've come in our journey at Beam and actually changing kind of some of the hearts and minds of the scientists and embracing lab automation. So, yeah.
So recently I was part of a discussion with a startup business. So automation, machine learning, and AI were their pillars. And they had automation, machine learning, but they had machine learning and AI with no automation. It kind of goes back to why we need you.
Yeah.
So I was wondering, like, how do you answer that question?
About why they need me? Oh, God, I don't remember what I said. I think I was just taken aback at first. I mean, I think one of the things that excites me, as we talk about like the pillars, you hear all the time, right? Automation, AI, machine learning being the things. At Beam, the questions we're answering a lot of times, AI is useful, right? But you can design the experiments to kind of directly answer the question of these phenotypic things. Maybe I'm wrong there, but you know, if you throw enough automation at it, you can do 20,000 experiments and cover the space that you might extrapolate through some machine learning models and some of the stuff we're doing. What excites me more, and this goes back to Marcus at Synthase, will appreciate this, is the design of experiment that it now enables. So, and I think what I told her is that with automation now, we're going to be able to not only let you answer the questions you know you want to answer, but even think about new questions you didn't even know you could, right? Like, can you now change the way you design your experiments to just get a dose response the first time? Can you get reps to actually power your statistics? Can you do things that manually you wouldn't even do? And so I don't remember exactly my answer, but I hope it was something along those lines of, like, you know, it's not that I'm going to make your life infinitely better, which hopefully I do, but it's going to make your science that much more explored and better understood. And at the end of the day, again, at Beam, we always bring it back to the patients. And so we're a base editing company. And so the more we understand about our science, the better we're actually able to develop the cures we're going after, and then ultimately cure the patients that we hope to cure. And so automation is a vital tool of that journey at Beam, and I know it is for all of your organizations too. Okay? I think we're good. Thanks, everybody, for your time this morning.